So we wanted to showcase some of the success stories of JCATI sponsored programs. So we assembled this distinguished panel to kind of share with you some of the work that they have done and the collaborations that they have created over the past couple of years, supported by JCATI. I ask you again to come to the microphones to ask your questions. And Dr. Candace Claiborne will be the moderator for this JCATI success story panel. Dr. Claiborne has been the Dean of the College of Engineering and Architecture since 2006 and is one of the few women engineering deans in the US as the Dean of WSU. As Dean, she has contributed to the growth of the college through several successful initiatives. She is the principal investigator on a $3.75 million NSF advanced grant that aims to increase representation, advancement of faculty, women in science, technology, and engineering, and mathematics. The grant is developing new strategies for faculty recruitment, retention, and advancement. She is also the principal investigator on a Department of Education grant to establish a program for recruitment, promotion, and advancement of women in science and engineering. During her tenure as a dean, several scholarships for women in engineering fields have been established. Dr. Claiborne has received several teaching awards in her department, including Outstanding Teaching Faculty in Civil Engineering in '94, the Leon Luck Faculty Award for the Most Effective Professor in Civil and Environmental Engineering in '98, and Outstanding Teaching Faculty in Civil Engineering in '99, and the Richard Crane Faculty Award for Distinction in Ethics Teaching in 2003. Candace, as she has repeatedly asked me to introduce her by her first name, received her BS in Chemical Engineering from University of Idaho in 1980. After graduation, she worked in the petroleum industry for Chevron and then for Atlantic Richfield Corporation. She returned to college at NC State, where she received her PhD in Chemical Engineering. Without further ado, Candace, please join me at the podium.
Thank you very much. Well, thank you all very much, and I'm very pleased to moderate this panel today. It should really be fun to talk about some of the emerging JCATI success stories that we have. I'd like to start by introducing the panel, and I have uneven bios from you all, so I'll do my best, and I may ask some of you to do your own introduction since I don't have information. But I think we'll start at the far end, and that's Mark Tuttle. Mark Tuttle is a professor of mechanical engineering in the Department of Mechanical Engineering at University of Washington, and he's the director of the Center for Advanced Materials and Transport Aircraft Structures. He received his BS, his bachelor's degree in mechanical engineering in 1975, and a master's degree in engineering mechanics in 1978, both from Michigan Technological University. And then he received his PhD in engineering mechanics in '84 from the Virginia Polytechnic Institute and State University. He joined the faculty at the University of Washington in 1985 and was chair of the mechanical engineering department from 2004 to 2010. Then his collaborator, let me get my notebook back, or my notes back out here. It's kind of short on space right here. Pardon me. This is Jim Simmons, who's a senior manager, I'm sorry for the delay,
no
from the Boeing Company. And Jim, I'll ask you to say a little bit about yourself, please.
Okay, I'm a graduate of the University of Washington, the ME department, right? Yeah, in the pre-Tuttle era. Yeah, I've been with the Boeing Company over 30 years. I've worked in, everything from the technology development, preliminary design side through support in the fleet, out on a ramp, you know, in the snow, trying to get cargo to load. I've worked on fighters. I've worked on commercial airplanes. So a very broad experience base. Delighted to be here today. Thanks.
Thank you. Our next panelist is Nicole Hoekstra. She's a professor teaching courses in the Plastics and Composites Engineering program at Western Washington University. She received her undergraduate and graduate education in mechanical engineering at the University of Minnesota. Prior to coming to Western Washington University, she worked as a manufacturing engineer at a thermoplastics manufacturing company that produces chromatography hardware, surgical instruments, and diagnostic equipment. Professor Hoekstra's research work always includes undergraduate students working with industry collaborators. Her work is primarily in the field of thermoset and thermoplastics processing, characterization of polymers, and tooling. And then I would like to, maybe you can introduce your collaborator and have him say a little bit more about himself.
All right. My collaborator is from Zodiac Aerospace, Jim Pinto, and I will have him introduce himself more.
I don't know nothing. I actually began working in industry, or actually for the U.S. Navy, Naval Table and Naval Research, in the late 70s on composite warfare and submarine hardware. We developed the composite bow dome for the submarine, the UK Trident, US Trident, back then. And Lockheed announced that they had the largest composite part in the world at 35 feet and 1,200 pounds. We had a 35,000 pound, 30-foot diameter by 7-inch thick composite bow dome, and we said, what the hey? 75,000 ton part that we believe was the largest and heaviest. I've worked in industry since then, since the late 70s. I have degrees in organic chemistry, mathematics, and thermodynamics. Being with the Navy, education was free, so it was easy to get those.
Then our next team, Amit Bandyopadhyay joined the School of Mechanical and Materials Engineering at Washington State University as an assistant professor in 1997 and was promoted to associate in 2001 and to the full professor level in 2006. His research is focused on additive manufacturing of functional materials. He has supervised or is supervising over 35 graduate students for their degrees in mechanical engineering, physics, or material science and engineering. He has published over 250 technical papers, holds 11 issued U.S. patents, and edited 8 books. He is a fellow of the National Academy of Inventors, the American Ceramic Society, the American Society for Materials, the American Institute for Medical and Biological Engineering, and the American Association for the Advancement of Science. And Amit, your partner is Christian Carpenter, who's the program manager from Aerojet Rocketdyne. Christian, would you say a little bit more about yourself, please?
Sure. So I graduated in 2000 from Auburn University with a Bachelor's of Aerospace Engineering, and went to work at NASA Glenn Research Center for 5 years, working on advanced propulsion technologies, and then came to Aerojet Rocketdyne in 2005. Still working on advanced propulsion technologies, actually for Roger. And so in the course of doing that, have gotten through a whole lot of electric propulsion, chemical propulsion, and various other platforms.
Okay, so these three teams have been chosen for a couple of reasons. They've had multiple years of awards through JCATI. It represents all of the universities that are involved in JCATI, and we're trying to highlight industry partners from around the aerospace industry in the state. So that's why this set of collaborators have been invited for this panel today. And I think I'd like to start off with a question, and then I invite you to come up and start other questions. So I guess what I'd like to start with is, how did the collaboration start in this case? Maybe better, how did the questions start?
Who are you directing the question to?
Well, we were instructed not to prepare any slides or anything, so this is going to be all ad hoc. The project that I'm involved with has to do with composite repair. And of course, the Boeing Company is using greater and greater levels of composites in not only in secondary structures, but primary structures of their aircraft. And repair, aircraft repair, is critically important. And consequently, there was an increasing need for techniques like that, and fundamentally, then I was already involved in composite work, and we saw a need, and that's how this collaboration began.
Yeah, when I think about it, and I wasn't there at the start of this, but I think about, let's just say in a fleet of 10,000 commercial airplanes, and we've delivered a lot more than that. Just average it out, 4 flights a day, 24 hours a day, it's something on the order of 1,700 gate releases an hour in the world. And so our ability to turn repairs quickly is really important. Lots of experience on aluminum airplanes. But we have, what, 1,300 or so 777s delivered now with primary composite structure in the tail. And I think we're up to 263 now on 87s. And so just the necessity of our ability to repair composites quickly, I think we're seeing good durability out of the systems, but our ability to move quickly is really important, and hence the importance of the work here.
You want to start?
Yeah, sure, I'll start. So in the space industry, we have a big challenge of accelerating, kind of as the last speaker from Boeing said, we have a big challenge of accelerating the pace at which we develop new products and get things to market. And in the space, especially in the propulsion side of it, it can take 12 to 18 months to get components in. So as you're trying to develop something, if you're waiting, come up with a concept and then you're waiting for a part for 12 to 18 months, it really slows down the pace of how fast you can get products to market. So we had a challenge that came out from the government to try to get satellite propulsion system time down to about 60 days. Which is a pretty enormous challenge. And so we started looking at, well, how would we really practically do that? And that's kind of when the additive manufacturing activities up here at Redmond got started. And when we were looking at that, we realized that there was basically a few steps in additive manufacturing that was going to really significantly impact the space industry. So the first step really is looking at how do we just take machine parts that we have and replace them with additive parts that we can get quicker for the purposes initially of prototyping and then in the future production. And then as you look forward, you say, well, that's good, that's a good thing, but really what we want is to be able to take this highly engineered system and get the cost and schedule down. And the way you do that is not just getting single piece parts, but really considering the entire system, including how you're making the parts, how you're putting the parts together, how joints are occurring and things like that. And so that had us start looking even further at multi-material printing, mainly of metallics. And so we did not have access to expertise in that area, to capital facilities in that area, and WSU had these facilities, and so that's when we contacted Dr. Bandyopadhyay.
Thank you, Candice, and thank you for organizing this and inviting me. I just want to highlight the point that Christian mentioned and few things. In academic world, we deal with graduate students. So the best thing we do is when we do something fundamental science, and the best thing the collaboration does is when it is tailored towards applied, something that we can see, has a benefit to it. So if you want to get a additively manufactured metal part, you can really send a part, and there are a lot of vendors who can actually build it. And that's not what we should be doing, and that's not what the JCATI program is. So we looked at this through the JCATI, how we can actually build multi-material systems that normally you cannot build it. So if you go to a vendor and say, I want this piece where the first half will be stainless steel, and the second half will be titanium, because the second half will see much higher temperature than the first half, they'll just stare at you and say, you are nuts, okay? But that's not what we do. We can build it to wonderful parts, stainless steel and titanium. How you joint it, that's really your challenge. And that's the kind of things, graduate students get excited, they say, hey, people couldn't do it, maybe I'll do it. And they'll spend the nights and we'll stand here and talk, okay? So that's the way how it works. It was painful, honestly speaking, because these two metals just don't go together, okay? And that's really what we were supposed to go out and do it. Most of the times we'll talk and share the frustration and see lots of failed parts, and one round, second round, third round goes on, and finally, one day they said, why don't you bring somebody, something foreign in between, that can kind of make the bond. And really that's what we did. At the end of the day, we actually produced something that you can actually hold it, touch it, feel it, where it's stainless steel and there is a bond layer in between and then titanium on top and things like that. For the graduate student, at the end of the day, all this great work should result into something, and the only thing that we care in the academic side is the publication. So in this case, there was a joint publication, and there was no problem in writing it and things like that. And that's, sometimes just working with a company can be challenging, but in this case, there was no problem. So essentially, it turned out to be, really good work. My co-investigator in this program is Sushmita Bose. She looked at the high temperature ceramics aspect, again additively manufactured, something that we normally don't do it. You go to a vendor and say, no, we don't do ceramics. You come, I'll do metal, I'll do plastics, but ceramic is a different beast. But that's what we do. Again, being in academia, we can do some of those fundamental work. For some reason, we took some moon dust or moon rock dust and built something. You can say why, I don't know, but people liked it. Lots of kids get excited and they say, can I work with this, because this is exciting. And again, we are in the educational system, so we should train them in the latest gadgets. And so JCATI helped us in a way doing things that we like to do the best, and Aerojet Rocketdyne helped us to kind of tailor it towards a direction that matters to them. So thank you.
We've actually been working with Zodiac Aerospace for almost 15 years when the JCATI opportunity came around. So one thing that's unique about our school up here on this stage is we're all undergraduates. And so it's really critical for students in my program, especially during their senior year, to work on a long-term project, hopefully with an industry sponsor. And so Zodiac's actually been sponsoring these kinds of year-long senior projects for our undergraduate students for a very long time. They sit on our industrial advisory committee. And so when the JCATI opportunity came around, immediately that was the company that we went to and said, this looks like a perfect pairing to put together a grant. And so in the 3 years that we've had JCATI funding, we've had over 20 students working on various projects. We've actually had 3 different grants in 3 completely different areas. We've had chemistry students working on polymer materials. We've had manufacturing students looking at new designs and processing. We've had material science students doing characterization. And so it's been a great interdisciplinary project on campus, but because Zodiac is so close to campus, we get to interact with them almost on a weekly basis and throughout the summer.
Add to that. So in the last 3 years, the projects we've had ongoing have been essentially, we gave them a panel problem that we had in our production. We told them that this production problem was seasonal, that it would come up once every spring and every fall and then fall away. And it would create huge production issues for us. The reason we gave them that wasn't so much we wanted them to solve it, but we wanted to introduce them to FAA regulations and to other things that were germane to commercial aircraft so that they would get this understanding and this feel as to how our business works. We know for a fact that this production problem that we have, that it occurs in one lot and then disappears for months. So it wasn't a huge problem for us. It was one that we never even attempted to solve ourselves because there was no reason to. By the time the problem resolved itself, you were back into trying to get your production back up to where it should be. So you didn't have the time to go back for it. But it allowed them to actually now see, oh, well, there's such a thing called flammability. This is a requirement for an aircraft part. This is something that we need to understand, and we need to know how the tests occur and what's necessary in order to have this happen. So we had this whole faction of students that were working on programs like that, and that was mainly the chemistry departments and the production and process people. Then we had the plastics technology people look at fasteners. A commercial steel fastener today is 80 cents a pound, whereas a composite fastener is $30 a pound. So if you can bring the cost down, you can actually save a tremendous amount of weight in your facility and your production and your delivered product. That's what the goal is. And they've done huge strides in redesigning some parts and modifying current plastic technologies for us.
Thank you. So we've heard a little bit about the projects that have been going on, and all of these have been a little bit longer term projects. I would like to invite questions from the audience, because if you don't ask, I'm going to keep on asking. So this is your time to come on up and ask some questions. I see Roger's moving to the microphone.
As you work through your collaborations, did you encounter barriers to the collaboration? You know, intellectual property is a classic challenge that, you know, between universities and industry that is, it's brought up on a pretty regular basis. And I'm wondering if the panelists could comment on whether or not that was a challenge for their collaboration.
I should mention I have a co-PI, Santosh Devazia, who's here today. And it happens in our case, again, we're working on composite repair. We had already submitted a patent application prior to the project starting. I should also mention, while Boeing is a partner, HeatCon is a second partner. HeatCon is in the business of composite repair. So what we're proposing is complementary to existing technology, and so far at least there's been no real issues with IP in our project at least.
Yeah, I guess the other thing I'd highlight there is that that's an industry capability that's going to have to be there, irrespective, you know, when you're talking repair or safety related things, irrespective of who built the airplane. We've got to have that capability out there in the industry.
We've worked on some new resin systems, and we've come up with some alternate designs for fasteners. And so there's a few key pieces in the broad team that we're on that have some intellectual property issues. But one of the things that I've been extremely amazed by is how generous Zodiac has been with almost everything else that we've developed. For example, we actually built a lab scale pre-preg manufacturing line at Western, and we're going to be starting to use that for coursework. And so all the students who go through my program are actually going to get to use that manufacturing process. And other organizations have approached us about using that manufacturing process for research that we'd collaborate with someone other than Zodiac. And so we've been able to add a lot of equipment capabilities, but also all of the knowledge that goes along with that that's really carrying into our program that Zodiac has allowed us to share with all of the students and make sure that that gets out there and really builds the knowledge base at our school.
We protect the things that are important to us, but we allow the things that are important to the industry as a whole to actually progress. There's no reason to hold back anything on a pre-preg machine when everything is public knowledge and out in the public domain anyway. So having a machine on campus that is essentially a mini version of the one that we use in production is actually great, and allows us to do a lot of things that we couldn't do otherwise. We didn't have the horsepower to generate test runs in our production facilities, but we can certainly do it on campus.
No, we did not face any IP-related problem, just to, but to be very honest, to make a collaboration productive, it's important to understand each other's need. So from our perspective, I think because we were doing the work, I superficially understood the space industry, not necessarily what, the nitty-gritty details. So after we got funded, the first thing I did make a visit, though we had many teleconferences and things like that, but I went there and tried to understand, sit next to each other, and then, talk. I think something like that, again, that probably more towards, WSU, because we are located on the other side. Some of you may need to find out, but, we are in the east side of it. So otherwise, I think we didn't have any problem. And in our case particularly, we are doing a lot of fundamental work, though there is, applications. But if there is any IP issue, I think it can be worked out very easily, because we are not focusing on a particular design, that's Aerojet's design. We are looking at the problem, and if there is any solution that we really come up with, I think there are standard protocols exist that we can follow.
Yeah, I'll just add that real briefly. In especially my area, we had to deal with ITAR, and the way that we did that was to take the problem that we had and boil it down to where it was a fundamental research project. So we didn't use anything that was, actual spaceflight designs. We took the general concepts and we said, how do we boil that down to a research project that Amit can just run with? And so that was sort of our approach, and that basically eliminated a lot of issues that would have been encountered with other approaches.
Thank you. Is there another question? Yes.
I guess I had a question a little bit related to the student experience of the teams that you were working with. It seems to me that what makes JCATI so unique is that it yields this ability to, to have the students be able to experience this really close integration between the work they're doing and the industry partners who are kind of consuming it. Now, traditionally, it seems like a lot of other funded projects I've seen where the academic PI sort of acts as this buffer between the students and then the actual quote-unquote client, right? You have the professors talking with the students, and then the professors talk with the funding agency, but the students seem to not really understand what they're working on here. And with JCATI, it seems that it's so nice because the students are directly seeing how their work is, interfacing with an industry partner. Now, I'm just curious why that model hasn't propagated, I guess, to other sort of, say NSF or, other types of funding projects. Could you maybe comment or contrast maybe, some of the challenges that maybe this presents, or why hasn't this JCATI model, in your opinion, kind of expanded to other types of funded projects?
Well, from my perspective, the JCATI program is a very good interface between academia and industry. If you talk about NSF, that's really academia and the government, and the actual customer, if you will, is the NSF. Often, and so there's not the natural link between an application and industry and the university professor or the graduate student or the students involved. I also think that it varies a little bit from one professor to the next. In my case, I think most of my students have interacted with the sponsor as much as I do, certainly with any Boeing project or industry-sponsored project. And that certainly has been the case with JCATI. There are two graduate students, both are here, Mahdi Ashrafi and Brandon Smith. I saw earlier, I think he's over here somewhere. And you'll be able to meet them later today at the poster session. And they both interact quite directly with Boeing engineers and with people at HeatCon. So,
I guess I could follow up. Are there additional challenges, I guess, that this additional interaction kind of brings apart on the part of the research project?
I don't know challenges. I mean, naturally, a student who starts a program is less involved or less knowledgeable, I guess, about background, and it takes a while to spin up a student so that they understand the industry and what the topic is about. So there's that level of introduction, but that's part of the education process, I think. So I don't think it's more, I don't see any big challenges there, per se.
I guess one of the things I like about this kind of cooperative research, where we have a more direct link to the students, is we go in and describe the need or the problem in general. I think it forces us to be more critical on the thinking that we do. And I don't know, I'm a big fan of involving people who don't know what they don't know into development. I'm probably set in my ways on a lot of things, and I've had my eyes opened by students more than once.
We actually have the opposite. The students are much more interested in working in industry-sponsored projects than faculty-sponsored research that may be funded by a grant like NSF. And I think it's because engineering students are very pragmatic and they see the ability to have that on their resume, to be able to have that as a conversation starter in an interview, to have that experience be able to open up doors for them. One of the things about students that come to Western, especially going into the plastics and composites engineering program, is a lot of them really want to go into the aerospace industry. And so one of the things that we do is we put together a very long list of projects that are available to students, and then they get to pick. And absolutely, the industry-sponsored projects are picked first. And so those are always going to be our very top students that get selected for those. So I have an NSF grant with additive manufacturing, and it's really cool, and I can make it sound really cool, but I still don't see the interest level from the students as much as the industry-sponsored projects.
We actually use it as a recruiting tool. So I couldn't tell you how many students from Western Washington are actually in our campuses and our facilities worldwide, but there are a large number of them that come to us after they graduate, and they begin to work with us. We started a partnership with them while they were still in school. They get educated into our system, and then when they come into our system, they hit the ground running, and they don't stop. They know what we want, they know how we want it, and they behave and work and respond tremendously. So I can't say enough about how that works for us.
You know, just to say, you know, my experience is it depends on the project, it depends on the student. I don't think there is any boilerplate solution. You know, we have been blessed receiving federal grants, state grants, industry funding, and things like that. Every project is unique, and some students can get involved directly and talk to the mentors and things like that. Some they just like to understand, they read literature, figure it out what are the challenges and how thing needs to be done. Also depends on the student. Some students want to get a master's degree, or undergraduate students just want to get that experience of research experience, get a paper and get into industry. Some students, they're trying to get into academia, they want to be a professor, they want to do things differently. I wouldn't say the NSF funded project that we have dealt with, or WNR funded or NIH funded projects that we do not deal with or talk to any industry members. Typically what we do is we try to bring our potential or current collaborators as seminar speakers, so that instead of sending them to on their site, bring the collaborator on our site and have long-term or long-range interaction. So the collaborator knows who the student is or who the students are, and the student also get to know, so that they can connect and contact and things like that. The fact of the matter is most of my students are smarter than I am, okay? And this is a different generation. I mean, it's fact, our 8-year-old kid knows more about Google than what I know, so they can go in, and so it's a different generation. So I think from again, it's a group culture. From my perspective, if a project gets funded, I share my proposal with my students, so they know what we have proposed, they know what needs to be done. I also tell them, you're my collaborator, you don't expect to show up in my office and say, what do I do tomorrow? You understand what needs to be done. We thought this is how we can solve this, but chances are you will find a better way to solve it. And fortunately, most of these people on the other side who are funding us, they're open. They would like to see something that is enriching, that is pushing the boundaries of science, that can help the students to think differently. So I wouldn't say how closely they're interacting with the mentor. I think how closely they're doing the good science is the most important thing. And good students, they do things just amazingly, and in the long run, you'll see them.
I don't really have too much to add, other than it was just really excellent to be able to go to WSU, see all the facilities, the creativity that the students were bringing, and the passion that they were providing there. And I think it's good for industry to get outside of the day-to-day and go see some of the really rapid innovation that's going on, and then bring that back to the company.
Great, thank you.
Another question? Yes.
Hi. I work for Seattle Goodwill, and I run the Youth Aerospace program. It's in the Everett, Marysville area, and we help high school youth complete high school and then go to Everett Community College and get a 1 or 2 year certificate in composite repair or machining, welding, CAD, aviation maintenance. And a lot of our youth have a lot of barriers. And when I go into the high schools recruiting for the program, it's amazing how many youth don't know about the careers in aerospace. I have to explain that we have 1,300 aerospace-related companies and thousands of jobs not being filled. And these kids, they have no idea. And so that's why we have this program. And basically, what we need, I think, is more internships or job shadowing or apprenticeships and more awareness in K through 12. We got a field trip to Aerojet. Thank you for that, by the way. And also Boeing is one of our sponsors, and that helps. But I think we need to do a better job of awareness, and I think people in this room are helping to do that. But I think we have a long way to go. And I'm thinking, what are your ideas to get youth more aware about these kind of jobs and help them succeed? So.
I'm sure you're aware of this, but the College of Engineering at the UW has held an annual open house. It used to be called open house, it's now called Discovery Days. We'll have probably 10,000 students on our campus this Friday and Saturday with the intention of highlighting engineering as a discipline, not necessarily just aerospace. But I hope that your students are aware of that program. And Mike Bragg is here today, or was here, and he is a big proponent of this. So I agree with you, though. I think in general, our K through 12 students don't think of engineering as, unless they have a mom or dad who's an engineer, somehow our culture doesn't push that or doesn't highlight that as a career path. So I agree with you, the need for that kind of outreach.
Yeah, when I think back to my childhood and trying to decide what to do if I grew up, and very exciting time. A lot of different companies engaged in aerospace. New airplanes every year to 2 years. The space race, all that kind of stuff. It's kind of damped out. There aren't nearly as many companies. There aren't the cycle time on a new product is much longer. So the shiny object isn't out there as much as maybe computers or something like that. I've taken groups of kids to the open house. The Hydroplane and Raceboat Museum down in Kent is starting a new education outreach that I think is going to be pretty cool. I think it's just finding that fascination with flight, and one of the things that struck me on the whole engagement with the students and research. Me and a lot of my colleagues grew up flying RC model airplanes. Our hobbies were all related to airplanes. Getting kids in the door towards things like that, I think, are another good way to go.
One of the things I've been excited about is the U.S. First Robotics Competition, the Mathlete. When I was growing up, that didn't exist. When I was going to college, that didn't exist. And I see that happening now in 6th grade. The kids are getting started, and then they get mentored up into the middle school. And those are obviously very focused types of skills. But I do agree with you. I don't know that as an industry we do a great job of educating about our industry and our discipline. I also think that if you don't have a family member in aerospace, I don't know that there's a huge population of students out there that are aware of the opportunities. I also think there's a big gap between engineering and the kinds of research and students that we work with, and then the trades. And building up the trades within Washington State is something that I'm hopeful will continue to improve, because there's a huge gap between high school diploma and a college diploma. And one of the things I'm very interested in is working with STEM educators at Western, putting together outreach opportunities that partner the STEM programs with the educators. Western is known for education more than anything else, and being able to put together some of those kinds of programs. So actually JCATI may be seeing another proposal coming forward that looks very different than what we've seen in the past, that's actually focusing more on outreach rather than on these technical disciplines.
Back when the old C&D company was private, we had a number of our employees that would bring their kids to work, and their kids would actually start working with us from the age of 13 on. We've had kids that literally grew up in our factories that knew everything about how to manufacture our components, that would be encouraged to go to school, then go to school, and then get a degree, and then come back and be successful as engineers, as managers, program managers, and then into executive management. So it always worked for us, but as we became a larger entity and then were acquired by the Zodiac Group and became more of an industrial company, there was less and less in that. And the main reason is you can't have a 13-year-old running around your factory for insurance and legal reasons. So a lot of that went away. And it's sad that it went away, but it had to. There's just too much liability there not to let it go. And we are guilty of not bringing or encouraging more kids to come into our companies on open houses. But one thing that we do is from the age of 16, when it's legal to get a work permit, we do allow students and kids to work in our factories during the summer as interns. So they'll work in our material lab and do testing. They're allowed to wander around the facility and see how other operations are working, but primarily it's the kids of people that work there. It's not so much the outer area of the community. If there were kids in the outer area of the community, they probably wouldn't be able to come in because we have a limited number of those internships.
It's a little different in Pullman because it's a small town and too much interaction. We have similar program that Mark is mentioning, that for high school students, competition and things like that. Myself and many other faculty members go quite regularly to, I have given even in elementary schools, to talk about things we do. Students come to our lab. If you look at high school, Pullman High School, there is only one high school in Pullman. So if you look at Pullman High School kids, quite a few of them actually work with professors, and actually some of them publish papers by the time they are finishing Pullman High School. That's fact, okay? So I think, I would say it's the STEM education as opposed to just aerospace. And if somebody in the Pullman community would like to know, I think they have plenty of opportunities. But I don't think, I can speak for the whole state. I'm sure things are different in other side.
Yeah, I'd say there's a couple things. One being that we've got to get our K through 12 educators really excited about STEM so that they want to learn more about it. And then we've got to help educate them on what the opportunities are and what the challenges are. So I go into elementary schools as well, do talks on various things. We shoot rockets off, or I bring in a 3D printer, or, things like that. And the kids really have a huge appetite for STEM related things. I think it's really interesting that Amazon released just a few weeks ago that STEM related toys was like the second largest area for Christmas of last year. And a couple years ago, I went home to my parents' house for Christmas and got my Legos out for my kids, and realized I didn't choose to go into space. Every single Lego that I had was space related, so I was set up from day one. So I think getting them access to just things that they can get hands-on experience with is really important. I do think. As you said, I think we need to get kids into the work areas so they can just at least see what's going on and make informed decisions about what they want to do with their careers. I think that's really important. So, but I think it starts with getting the K through 12 educators excited about STEM.
Thank you.
Thank you for the question. I see that Miran is hovering back here, so we'll have to stop now, but I would like to thank all the questions from the audience. They were great questions, and thanks to the panelists as well, and then we'll stop for a coffee break and networking, but thank you very much.